So per se, what we are doing in all these tests is the purpose of all these different methods is different. It is not like we are doing the same thing with different methods. The purpose is different. Static bearing capacity equations are standard, like what it just tells us about the load of our like load carrying capacity. In this, what we are doing basically is what we are calculating based on the SPT and the CPT values. We are either calculating the F value, frictional resistance value, or we are calculating the CU based on the CPT test and bearing capacity. So based on this, we again stick these results in our main formula, and then we calculate the resistance. So in field load tests, what we are doing is they are we drive a test pile basically. How can I put this? The purpose of this test basically is to determine the vertical or uplift or lateral load capacity of a single pile or a group of piles, and to determine the settlement, and to verify. It is basically a verification test, we can say. Verification with what we have already calculated. And okay, so you must have studied that before driving a pile in the field. We do a test, pile test. This is the test that we do in the laboratory. And then the dynamic method. Dynamic method is at the start of the pile driving exercise. It gives us some information according to the hammer that we are using for the purpose of pile driving. It gives us uh, an information based on the resistance offered by the soil to the penetration during pile driving. It's an indication to its bearing capacity. Um, So, in order to develop desired load capacity, point bearing piles must penetrate into the dense soil layer sufficiently. But it cannot always be satisfied that the penetration depth is exactly reached, because soil profiles may vary. I have dug a borehole here, but then the soil profile may be a little different here. So, dynamic equations are used to determine whether the pile has reached satisfactory bearing value at predetermined length or not. It is a verification test. Okay, so let us move on to our first question then. The results from SPT test in a granular soil deposit are given below. A concrete pile 9 meter long with square cross-section area of 0.3 cross 0.3 meter is driven into the sand. Estimate the allowable load carrying capacity of the pile. Okay, let us start with this question. Mm, Just opening the file will take just 2 minutes. It's taking awfully long. I think my computer is a bit slow today. I will. Okay, so it's here. Okay, is this the same question? No, actually, it's not 1 minute. Okay, so, oh, I'm sorry, this was the first question. I was thinking what happened. Okay, so let's start then. Let us first, as I always mention, let's draw the diagram of our question. A driven closed pile of length 20 meter has a circular cross section of diameter 0.5 meter. Let us draw a pile. So the diameter is 0.5 meter, and it is laid down in a layered deposit. And we have been given two layers. This is layer 1 and this is layer 2. The depth, complete depth of the pile is 20 meters. Okay, so the properties of uh, soil are given below. Let's write it in some other color. Okay, so for layer 1, gamma equals 16 kilonewton per meter cube. Phi equals 32 degrees and the thickness is 6 meters. Gamma sat 18.5. For layer 2, gamma is 20, phi is 40, thickness is thickness of the layer actually doesn't matter that much. We just need to know this will be 20 minus 6, which will be 14 meters. Otherwise, the whole thickness is 25 meters. But we only need to focus on the thickness embedded depth. So let us call this gamma saturated because it is mentioned that The table is 3 meters from the surface. Groundwater table is 3 meters from the surface, and this is more likely a gamma saturated value because normal gamma value is about 17, 18. Above that, it is okay. So this is our groundwater table at 3 meters. So let us proceed to solve the question. First thing is we need to calculate the ultimate point load resistance. You see, ultimate point load resistance, I told you it will be CNC plus QNQ, isn't it? And we ignore the gamma B and gamma. Now, because it is a sandy deposit and C is zero, this term goes to zero. Now we have Q and Q, but for this we have two sets of values. Which value to use will depend in which strata this pile is ending. Since this pile is ending in the second layer, our values would have are supposed to be from those of the second layer. If the soil was ending in first layer, for example, just here, then we would have taken the values from layer 1. So uh, this point resistance thus will be calculated from layer 2. Properties. Okay, now we know our QP equals the load will be area into our bearing capacity. The load will be area of the bottom of the pile or the top of the pile multiplied by our QP, point bearing resistance, and our QP will be overburden. QP will be Q and Q, where Q is our overburden pressure. Overburden up till here. So it will be, let's call this gamma 1, gamma sat 1, gamma sat 2. It will be gamma 1 times 3 plus gamma saturated 1 times 3 plus gamma saturated 2 times 14. So this will be our overburden. Not saturated, actually submerged, because we're taking effective. We have to take the effective values. In our calculations. This will be equal to 16, 18.5, or not 18.5, minus, let's take gamma w as 10. There is a multiplied by 3 here. So let's calculate this. This is 48 plus 25.5 plus 140. So our Q dash will be 213.5 kPa. Let's move to the next page. Let me delete all this. Only this part. So our Q dash came out to be 213.5 kPa. So our QP will be equal to area AP. Oh, we also have to calculate the uh, um, NQ. Oh, Q dash is okay. So using Meyerhoff's equation, Meyerhoff's chart, for example, for phi equals 40 degrees, let me check the value of NQ. So Meyerhoff has given different values of NQ for piles and different for shallow foundations. So it's not exactly Terzaghi's equation. It is the same equation. The only thing is that the values have changed a bit. And you must understand that the values had to be changed because the load transfer mechanism is changing. Uh, we cannot use the Raghi's factors here because when we were discussing shallow foundations, we actually discussed that the Raghi's relation is only good for shallow foundations, while Mayer-Hauss equation was good for both shallow foundations as well as deep foundations. So if I draw, so basically, besides Meyerhoff, Vesic has also given his theory for pile foundations. Uh, Terzaghi, if we let me draw the diagram first. Okay, so Meyerhoff has given this kind of failure envelope for end bearing resistance. Let me draw it again. Oh, something like this. I'm not getting this. I'm not able to draw it correctly, so it is better you refer to your books for this. And on the other hand, Vesic has given this kind of failure surface. So according to Vesic, basically, punching shear failure occurs in deep foundations, irrespective of the density. There is a plastic zone here. This is the elastic zone. So according to Meyerhoff's theory, this is the uh, failure surface that Meyerhoff has given, and then he has given the different values for NC and gamma in for piles. Uh, but for the frictional resistance, okay, we'll talk about it when we talk about frictional resistance of the pile. Let's move on forward with the discussion on the point bearing resistance first. Uh, so NQ in this, from the graph that Meyerhoff has given, is 346. So RQP equals AP into Q dash into NQ, which is equal to pi by 4 into 0.5 square into 213.5 into 346. This comes out to be, I calculated 5 by 4 into zero point 0.5 square, 213.5 to 346. So our QP equals 14505 kilo Newton. So this is for QP. Now let's go to our QF. So you see our QF, we take it as, let me say QF, area for the friction angle into our F. So the problem with this is that the area will be perimeter into length. The problem with this is that it is directly proportional to the length of the pile. Does that mean that if the pile is infinitely long, that there will be infinite resistance? It is not possible that by only increasing the length of the pile, there is this buckling effect also. By only increasing the length of the pile, we can get higher and higher values of frictional resistance. So Meyerhoff has given the concept of critical depth, up to which, uh, if the length of the pile continues up to that depth, This resistance will linearly keep on increasing, but beyond that, it will not increase, neither decrease. Actually, it will remain the same. So, up to certain critical depth, let me write LCR, our frictional resistance will directly be proportional to L. But beyond this, the frictional resistance will remain same. So the first task for finding the QF will be to determine what the critical depth is. Critical depth, according to Meyerhof, is about 15 times the diameter of the pile. And here we can say it is 15 times 0.5, which is actually 7.5 meters. So what we will do is we will find the distribution of this resistance and actually calculate the area. Up to 7.5 meters, there will be a linear increase, and beyond that, it will remain the same. So this will be 20 minus 7.5, that is 12.5, I think. Yes, 12.5. Okay. Excuse me. So we can either, it will be the same thing, but what we can do is we can take the average of the frictional resistance here, because what we will be doing is we will be dividing it by 2, uh, or and the full frictional resistance here. So let's calculate. Let's draw the strata. We know at 6 meters. I don't know why I'm so bad at it. At 6 meters, we have a different strata, and K has been given as, by Meyerhof, K has been given as, sorry, not K, F. F has been given as K sigma naught dash tan of delta. K is the earth coefficient pressure at rest. You might uh, think of it in a way that obviously K will, so if we take this overburden pressure and K, this has to be there because we're talking about the not the vertical resistance we were talking about in the point bearing. Now the lateral resistance. So the soil is pushing towards this. We will talk about the lateral pressure, and lateral pressure is what? It's vertical pressure multiplied by our coefficient of earth pressure. And since the soil is not moving, it will be coefficient of earth pressure at rest. And what we are doing actually is just simply frictional resistance when we calculate, like there is a block and then there is a normal force, and then this force is equivalent to N is equivalent to um, then this frictional force is equivalent to normal force multiplied by tan delta. So we are calculating the normal force on the sides of the pile, which is basically the lateral force in the soil, which is the normal force in the direction of the motion of pile. The pile is supposed to go like this, and normal to this we have this lateral force. So this multiplied by the tan delta, we get the frictional force. So that is basically what we are doing. And delta is the friction angle between the soil particles and the uh, um, uh, what we can say, the pile. So you will have different delta for concrete, different for steel, different for timber, based on the material of pile you are using. Okay, so let us calculate K. Let's take K. Now we will have different K for this layer and different K for this layer because they are different. So K1 will be 1 minus sine phi 1. Usually there is a convention that for driven piles, let me write it here. We take K naught equals 1.4 times 1 minus sine phi dash. Just let me check from my source. Okay, let me write it in a different slide. So our pile type, if it is bored or jetted, our K is approximately equal to 1 minus sine phi dash. If it is a low displacement driven pile, Low displacement driven pile are the piles that are open-ended, which do not uh, close at the end. Because if the pile is closing at the end and then you are driving with a hammer this pile into the ground, what will happen is that it will dislocate a lot of soil. That would be a high displacement pile. But a low displacement pile is when you have an open-ended pile which just cuts into the soil. The perimeter just cuts into the soil and then you remove this portion. But in a closed end soil, you will have closed end pile, you will have a lot of displacement of material. What will happen is that a lot of this material will be displaced to the sides. So for low displacement piles, it is about 1.4 1 minus sine phi dash. And for high displacement driven piles, it is about 1.8 times 1 minus sine phi. And the excuse me, and the delta that we are supposed to take, if not given, then we take the delta equal to 0.5 to 0.8 times phi dash. Right, to, not minus. Okay, so let's see the question here. It is a closed-ended pile, so it means that it is a high displacement pile. So we will take, instead of 1.4, we will take 1.8 here, because that is what the convention is. High displacement pile 1.8 times 1 minus sine phi. So let's calculate it then. This is equivalent to 1.8 times, for the first layer, it will be 1.8 times 1 minus sine of 32, and for the second layer it will be 1.8 times 1 minus sine of 40. So let us calculate. Okay, so let us do one thing. Let's draw a table, because what we will do is we will find the frictional resistance of each segment, the first layer, the second layer, even. And then Let's draw the overburden diagram first. This is at 6 meter. This is at 3 meter. So this will be K1, gamma 1. Let's let this be H1, H2, H3, H1. And then there will be the water table. This portion will be K1, gamma 1 dash, H2. And then we have this constant portion. This will be K2. Okay. At 7.5, I have to take the constant because the critical depth is up to 7.5. Then this portion will be K2, gamma 2 dash. It's H3. And then we will have this as the summation of these three, if it makes sense. Overburden, let's calculate. Uh, Actually, we're calculating overburden times the K, so horizontal stress. So total lateral stress we will times K. Let me see. For segment 1, 2, 3, and 4. So here we are changing layers. Okay, let me draw the table now. Okay, let's write the Z, which is the depth, and then we take the height, then we take the gamma, we take the gamma dash, we can take the phi, and from phi we can calculate the K. Okay, so this is from 0 to 3, this 3, this is 3 to 6, 3, and then 6 to 1 point to 7.5, which is 1.5, and then 7.5 to 20, which is 12.5. The gamma in the first layer is in